Alright, so we learned solution space of the system Ax is equal to B. We looked at Ax is equal to B, where A was m cross n, fine. So, that was about the rectangular matrices. Now, we want to concentrate only on square matrices. So, for us in this lecture, we are going to have A is n cross n, alright, a square matrix, and want to understand whatever we have done till now as far as this matrix is concerned, alright. So, there is this theorem which I would like you to understand, theorem is very important theorem, which relates all the ideas that I had till now about matrices, fine. So, the following statements are equivalent. Following statements are equivalent for any square matrix. A of n cross n, fine. The first statement is A is invertible. We had learned this, what is invertible. Second, the homogeneous system Ax is equal to 0 has only the trivial solution, only the solution. So, recall that trivial means only the trivial means 0 is the only solution. Alright, is the only, so there is no non-zero solution. Alright, 3. The row reduced echelon form RREF of A is identity. Fourth, A is product of invertible matrices. Five, the system Ax is equal to B has a unique solution for every B. 6, the system Ax is equal to B has a solution or consistent for every B. All right. So, let us look at the proof of this. What we would like to say here is that, see, if I look at 5 and 6, 5 says it is a unique solution, the second says I do not have to worry about uniqueness. All right. I do not have to worry about uniqueness. Basically, we are saying this because what happens is that in lot of problems, it is very difficult to prove that something is unique, fine, but it may be easy to find the solutions for in each case. All right. So, showing uniqueness can be difficult, but if I can show that there is a solution for every choice of B, then I have that A is invertible. All right. So, these are basically to help you get things without doing much work. All right. So, let us try to prove them. So, 1 implies 2. So, 1 implies 2. So, we are saying that A is invertible implies the system Ax equal to 0 has only the trivial solution, fine. So, A is, so let x naught be a solution of Ax is equal to 0, fine. So, this implies Ax naught is 0, fine. So, now let us look at x naught. X naught is same as identity times x naught. Now, we are saying that A is invertible. So, I can write identity as A inverse A times x naught, which is same as A inverse of A x naught, which is same as A inverse of 0. This is what we get from here, which is 0, all right. So, x naught has to be 0, you do not have a choice other than that. So, it has only the trivial solution, fine. Now, let us look at 2 implies 3. The 2 says that the system has only the trivial solution, fine. What does it mean? Only the trivial solution means trivial solution of A x is equal to 0. What does it mean? This implies that the system has no free variable, all right, because if a system has a free variable, then it has infinite number of solutions, but here it says that it has only the trivial solution, there is only one solution. So, there is no free variable, and this implies every variable is a basic variable. Is a basic variable. And now, where are the basic variables? The basic variables, they come from pivotal columns, all right. So, we are saying that every variable is a basic variable, means that every column is a pivotal column, implies every column of RREF of A is a pivotal column, fine. There are n of them and there are only n equations, and therefore, what you get is, so all right, so everything is pivotal, means I can write this as 1 0 0 0 0 1 0, because every column is a pivot, all right, 0 0 0 and 1. So, this is a pivotal column, this is pivotal column, each of them is pivotal column, each column is pivotal, fine. And therefore, so this is the RREF of A, and this corresponds to looking at that RREF of A is equal to I n, fine. So, this is what we want, the row reduced echelon form of A is I n. Is that okay? So, again let us go back, understand it. We want to prove that 2 implies 3. So, 2 says the homogeneous system has only the trivial solution. Since it has only the trivial solution, it means that the system has no free variables. It has no free variables means it has only basic variables. So, there are n basic variables. Now, each basic variables corresponds to a pivotal column, and therefore, each column is a pivotal column, and therefore, this is the matrix that you are going to get, because the matrix is n cross n, fine, which is I n, fine. Now, once you have that, so this is what it was, the row reduced echelon form of A is I n, so we have proved that part. Now, let us look at 3 implies 4. So, we are saying that RREF of A is I n, but what is RREF of I n? To obtain RREF of I n, we need to multiply by elementary matrices on the left. That is the way we get, we have to apply the Gauss-Jordan algorithm, elimination method. So, what we are saying is that we have got E1, E2, Ek times A is identity, and this implies that A is nothing but inverse of this matrix, which is E1, E2, Ek inverse, all right. A is inverse of this, which is same as Ek inverse, Ek minus 1 inverse, so on, E2 inverse, E1 inverse. Is that okay? Now, what we know is that if E is an elementary matrix, its inverse is also an elementary matrix. So, each of them is an elementary matrix, and therefore, we have shown that A is a product of, this implies A is a product of elementary matrices. Is that okay? Now, let us prove 4 implies 1. Fine. So, what we 4 says that A is product of elementary matrices. So, A is equal to some E1, E2, EL for some elementary matrices E1, E2, EL. We have to prove that A is invertible. Now, what we know is that each of them is invertible because they are elementary matrices, invertible matrices, and product of invertible matrices and product of invertible matrices is invertible implies A is invertible, and nothing but A inverse is equal to E1 to EL inverse, which is EL inverse EL minus 1 inverse till E1 inverse. Is that okay? So, we have been able to show that A is invertible because you could write A inverse as product of invertible matrices. Is that okay? Fine. Now, let us try to prove 1 implies 5 and 5 implies 6. So, 1 implies 5. So, 1 says that A is invertible, that is given to me, and 5 is that the system Ax is equal to B has a unique solution. For each B, all right. So, let x naught be a solution. So, here we already know that x is nothing but A inverse, or x is equal to I times x. Now, A is invertible means I can multiply it by A inverse A of x, which is same as A inverse of Ax, which is A inverse of B. So, this is the unique solution. Fine. X is equal to A inverse of B is the unique solution. Now, 5 implies 6. 5 says that the system Ax is equal to B has a unique solution for every B. 6 is the system Ax is equal to B has a solution for every B. What does it mean? We are not talking of a unique solution, we are just saying that there is a solution. 5 says that it has a solution, and not only it has a solution, the solution is unique. Fine. So, 5 directly implies 6 because it is the same statement other than removing the uniqueness. Fine. So, 5 is more stringent as compared to 6, and therefore, 6 directly follows from 5. This is just a same statement after removing uniqueness. All right. So, it is even a lighter one. Fine. Now, let us try to prove 6 implies 1. So, we have been given that the system Ax equal to B has a solution for every B. We have to prove that to show A is invertible. Fine. So, here we will use the idea that the homogeneous system Ax equal to B has a unique solution or things like that. Fine. So, we have to show that A is invertible. So, let us consider this part that is given to me. So, now let us consider the system Ax is equal to E1, which is 1 0 0, Ax is equal to E2, which is 0 1 0, and Ax is equal to En, which is 0 0 0 1. So, let us consider these n system of equations, n systems of equations. Is that okay? So, you are not considering one system, we are considering n of them, where the B is E1, these are E1, E2, En are the different choices of B that I have. Fine. Now, what we have been given that the system this has a solution for every B. It means that there is a solution for E1, say x1. So, this is the solution. Fine. For E2, B equal to E2, I again have a solution x2. For B3, I have x3, B4, x4, and for B equal to En, I have xn as my solution. So, what we are looking at is I define B is equal to x1, x2, xn. Then A times B will be equal to A times x1, x2, xn, will be equal to A x1, A x2, A xn, which is nothing but E1, E2, En, which is equal to A times, or which is same as identity. Fine. So, you have got AB is identity. Fine. Now, from here I would like you to see that A is invertible. Fine. So, how do I go about it? So, consider the system Bx is equal to 0. Consider the system Bx is equal to 0. I am not looking at the system Ax is equal to 0. That is important. I am looking at the system Bx is equal to 0. Fine. So, here what you see is that if x naught is a solution, then x naught is same as I times x naught. Now, but we just proved that I is A times B. So, I is A times B of x naught, which is A of B x naught, which is A times 0 is 0. So, what we are seeing is the system Bx is equal to 0 and B is a square matrix. System B is equal to 0 has only the trivial solution. Is that okay? Since it has only the trivial solution, so by what we had proved that 1 implies 2, 2 implies 3, 3 implies 4 and 4 implies 1, the first part, all right, implies that B is invertible. All right. So, what we have done is that we have started with A, we have got a B and we have shown that B is invertible. Now, since B is invertible, its inverse is unique, and since A times B is identity, so the invertibility of B will imply that BA is also identity, because AB is identity. Yeah? All right. And these now together, so together that AB is equal to identity is equal to BA implies A is invertible. Fine. So, what we have done is we could not prove 6 implies 1 directly, we have to go from A to B. So, we formed another system Bx is equal to 0 and use the previous part to prove that A is invertible. Is that okay? Those are the things, small tricks that you need to understand, but what it says is, which is very important, is that you do not have to worry about trying to prove AB equal to identity equal to BA whenever A or B is a square matrix. Just one side is enough to conclude that everything is nice as far as the invertibility is concerned. Is that okay? So, now some corollaries related with these ideas which are very important. Corollary. So, first corollary is what I have just stated. So, let me write it again. So, let A be M cross M matrix over C or R, that we are not bothered. Then the following holds. One, if there exists a C n cross n, sorry, here it was M, so M cross M, such that CA is identity implies A is invertible. 2, if there exists a B M cross M such that AB is identity implies A is invertible. All right. So, the idea here is that whether you can get the left inverse or the right inverse. So, either left inverse or right inverse, we get inverse. All right. So, the idea here is we are looking at system of equation, it is a square matrix, and therefore everything goes nicely. Fine. Another corollary. So again I have the square matrix Ax, I have a square matrix A n cross n. Fine. Then the two statements cannot hold together, What are the statement? The first statement is the system Ax is equal to B has a unique solution or has a solution for every V, and B part, let me write 1 and 2, I think 1 and 2 like this. The system Ax is equal to 0 has a non-trivial solution. All right. So, understand that when I say the system A is equal to B has a solution for every B, it implied that A inverse exists. This is what we proved. 6 implies 1. This was 6 implies 1. All right. Now, here it says the system A is equal to 0 has a non-trivial solution. What we have shown is that if A is invertible, then we have only the trivial solution, that was 1 implies 2. So, this is a contradiction to 1 implies 2. Is that okay? So, that is the way it helps things to all right. Another corollary is what is called the theorem of alternatives. That only one of them can happen. All right. Again, the two statements cannot hold together. The two statements cannot hold together. Is that okay? So, what are the statements? 1, the system Ax is equal to B has a solution. Again, important, A is n cross n and everything, so a square matrices only. 2, the system y transpose A is equal to 0 transpose and y transpose B not equal to 0 has a solution. So, we are talking about two system of equation. One is looking at the system Ax is equal to B. So, I am solving the system from the right and looking at Ax is equal to B, and the second is looking at the solution of y transpose A equal to 0 transpose, homogeneous system. Again, this is a homogeneous. Fine. But we are also requiring that I want only those solutions for which y transpose B is non-zero. All right. Solutions with non-zero condition. All right. And this will also come back to this when we will look at what are called fundamental spaces and do some things there. What we are saying is that if I want a solution of the system Ax is equal to B and at the same time a solution of the system y transpose A is 0 transpose, or a homogeneous system with y transpose being non-zero, that is y and B are not orthogonal, they are not perpendicular, all right, then there is a problem. I cannot get both of them together. And the proof is simple. So, let me write the proof. So, what we have, so let Ax is equal to B have a solution x naught. So, this implies that A x naught is B, fine. Let y naught be a solution of y transpose B, y transpose A is equal to 0 transpose, fine. So, now I have a solution here. So, this implies that y naught transpose A is 0 transpose. Let us compute y naught transpose B, all right. So, y naught transpose, what is B? B is A x naught, which is same as y naught transpose A of x naught, but y naught transpose A is already 0 transpose times x naught. So, which is 0 0 times x naught, which is 0. Is that okay? So, what we see is that as soon as I have a solution of x naught here and a solution y naught here, their dot product or their product y naught transpose B is 0, fine, but we wanted a solution, y of y transpose A equal to 0 transpose with y transpose B being non-zero, all right. So, that is a contradiction. Is that okay? So, this is the thing why it is called system of alternatives, basically because of this, that so this is called system of alternative, because what it says is that if you want both the solutions, then both the solutions are not possible. Either you have a solution of A x equal to B, or you have a solution which looks like this, which is a solution of the homogeneous system, but of y transpose A, not of A x. Is that okay? There is a difference between y transpose A and A of time A times x, all right. So, be careful, this idea of theorem of alternatives appears again and again at different places, fine. So, this is the end of this lecture, and we will look at the next time in what are called determinants and try to solve the system using determinants and look at equivalent conditions. That is all. Thank you.